Welcome everyone to the next video lecture in our Predictive Analytics course. I am Dr. Shiva, Assistant Professor in Department of Computer Science and Business Systems, the Araja College of Engineering, Madurai. In the previous video, we introduced the concept of decision tree and understood why the decision tree are important in the predictive analytics. We also discussed how decision trees belong to family of supervised machine learning algorithms, where the model learns from historical data for which the target outcome is already known. In today's lecture, we are going one step deeper. Our topic is decision tree terminologies and tree constructions. Let us begin. Before starting today's topic, let us quickly look into where we are in the predictive analytics course. We are currently in module 8, decision tree. This module consists of several important topics. We begin with introduction to decision tree, then we move to decision tree terminologies and tree construction, which is today's topic. Let us look at the major concepts that we are going to cover in today's lectures. First, we will understand the decision tree construction overview. Then we will identify the different nodes in decision trees. We will learn what a root node is. Then we will understand decision nodes and leaf nodes. Next, we will discuss tree level and tree depth. After that, we will understand the splitting process. Then comes one of the most important concepts, node impurity. Once you understand the impurity, we can introduce entropy. Entropy helps us measure uncertainty in the data. Then we will learn about information gain, which helps the algorithm select a good splitting attribute. Finally, we will study the Gini index and stopping criteria. So the lecture moves gradually from structure of a tree to mathematics behind the tree. Decision tree construction overview. Let us first understand the overall idea of decision tree construction. A decision tree is not created randomly. It is built systematically by selecting the best attribute at each stage. Suppose we have a dataset containing information about customers. We may have attributes such as income, age, credit score, employment status, and existing loan. Our target variable might be loan is approved or not. The algorithm needs to determine which attribute should be used first. Should we start with income? Should we start with age? Should we start with credit score? Or should we start with employment status? The algorithm evaluates the available attributes and select the one that provides the most useful separation of data. Once the first split is created, the same process is repeated for resulting subsets. This repeated division of the data is called recursive partitioning. So the basic process is select an attribute, split the data, evaluate the resulting group and repeat. The process continues until the meaningful and sufficient pure groups are formed. Root node. Now let us discuss the first important terminology, root node. The root node is the first and topmost node of decision tree. It represents the entire data set before any splitting has taken place. Every decision tree has exactly one root node. Let us understand this with a simple example. Suppose a bank has a historical information about customers. The dataset contains customers A, B, C. The income may be high, medium, and low. The loan is either approved yes or no. So take this example. Initially, all the three customers belong to one dataset. The algorithm evaluates the available attributes. Suppose it determines that the income provides the best separation, then the income becomes the root node. We can represent it as income. From this, the root node different branches are created. For example, high income, medium income, and low income. These three options can be created as the various branches of the root node. The important point is that the root node represents the entire training data set. It has no incoming branches. In the same, it is the starting point and it is selected based on the appropriate splitting criteria. So the root node is the starting point of a decision tree. After the root node, we have decision node. A decision node is an internal node where the dataset is further divided based on another condition. In simple words, a decision tree asks another question. For example, age greater than 30, or credit score greater than 700, or BMI greater than 25. Each question divides the record into two different groups. Let us consider a loan approval example. The root node might be income is greater than 50,000 or not. If the answer is yes, the algorithm may ask another question. So credit score is greater than 700. That's the second question in the decision node. Therefore, the decision node represents the intermediate decision in the tree. It usually has one incoming branch and two or more outgoing branches. Depending on the tree algorithm, the process continues until we reach a leaf node. So basic sequence is root node, decision tree, decision node, leaf node. Next, leaf node. Now we come to another very important component is leaf node. A leaf node is a terminal node of decision tree. A terminal means that there is no further splitting after this point. The leaf node contains the final prediction. For example, in a loan approval problem, a leaf node may contain loan approval or loan is rejected. In a healthcare application, a leaf may contain diabetics are healthy. In fraud detection, it could be fraudulent or genuine. Let us consider this example. Simple structure. If a customer satisfies this condition, income is greater than 50,000 and credit score is greater than 700, the tree may reach loans approved. That is the leaf node. Tree levels and depth. Next, let us understand two related concepts. Next, let us understand two related concepts. A tree is organized into different levels. The root node is normally considered the starting point. As we move downward, we encounter child node at subsequent levels. For example, level 0 root node, level 1 child node, level 2 decision node, level 3 leaf node. Now let us understand tree depth. The tree depth is the length of the longest path from the root node to the leaf node. For example, if the longest path contains 4 edges, the depth is 4. Depending on the convenient, it is used as implementation. Why is depth important? Because depth indicates the complexity of the tree. A very shallow tree is simple. A very deep tree contains many decisions. A very deep tree may learn extremely specific patterns from training data. This can result in overfitting. Therefore, controlling tree depth is important part of decision tree modeling building. We will discuss this more and we will study the stopping criteria and pruning. Now we reach the central process in decision tree construction, splitting. Splitting means dividing a dataset into smaller subsets based on value of an attribute. Let us take an example. Suppose we want to predict whether a customer will purchase a product or not. We have attributes such as age, income, membership, and previous purchases. The algorithm needs to decide which attribute should be used to split the data. The process generally involves several steps. First, we select the candidate attribute. Second, we divide the database on the attribute. Third, we measure the impurity of the resulting group. Fourth, we compare the result for different attributes. Finally, we choose the best split. Then the same process is repeated recursively. So the complete process is select, divide, measure, compare, choose, and repeat. The goal is to create a child node that are more homogeneous than the parent node. It is important to understand that not every split is good split. A good decision tree chooses splits that create pure child nodes. Let us understand what we mean by pure. Suppose a node contains 10 records. If all the 10 records belongs to the same class, such as 10 approved and 0 rejected, then the node is completely pure. Prediction becomes very easy. On the other hand, suppose the node contains 5 approved and 5 rejected. This node is highly mixed. It is difficult to make a confident prediction. Therefore, a good split should move us from a mixed parent node towards more homogeneous child node. For example, parent 5 yes, 5 no. After good split, child 1 is to 5, that is yes and 0 no. Child 2 will have 0 yes and 5 no's. This is an excellent split. Child 1 will have 5 yes and 0 no's, and child 2 will have 0 yes and 5 no's. Now, let us introduce the concept of node impurity. Impurity tells us how mixed the classes are within a node. If all records belong to one class, the node is pure. Therefore, impurity equal to 0. If all records are evenly distributed, then it is impurity. For example, half in yes and half in no. If it is this case, then it is called as the node is impurity. So consider this, take this as an example. In node A, the disease, there are three outcomes of the disease. All the three are healthy. If you take node B, one is healthy, one is diabetic, another one is healthy. So there are mixed of results possible from node B. So it is not pure. The impurity is high here. So this is called node impurity. If a node result into only one result, it is highly pure. If not, it is impure. Entropy is one of the most important mathematical concepts in decision tree. Entropy measures the amount of uncertainty or disorder in the dataset. In simple terms, it tells us how mixed are the classes in the node. If a node contains only one class, there is no uncertainty. Therefore, entropy equal to 0. If the classes are evenly distributed, uncertainty is high. For a binary classification problem, the maximum entropy occurs when two classes are equally likely. The formula is entropy is equal to minus summation of pi log 2 of pi. Here pi represents probability of each class. Don't don't worry if the formula looks complicated initially. The concept is more important. Entropy measures uncertainty. How low the entropy means the node is relatively pure. How entropy means the node is mixed. So low entropy means the node is pure. High entropy means the node is mixed. Decision tree algorithm uses entropy to compare possible splits and identify which split reduces the uncertainty the most. Let us now calculate entropy using a simple example. Suppose we have 8 loan applications. 6 are approved and 2 are rejected. Therefore, the probability of approval is 6 divided by 8, which is 0.75. The probability of rejection is 2 divided by 8, which is 0.25. Now we substitute these values into entropy formula. Entropy is negative of 0.75 log base 2 of 0.75 plus. So 0.25 log base 2 of 0.25. When we calculate this, we obtain approximately 0.811. What does this value mean? It tells us that the node still contains some uncertainty. It is not completely pure because we have both approved as well as rejected records. Now imagine that all the 8 applications were approved. and the probability of approved is equal to 1 and the probability of rejected is equal to 0. The entropy would become 0. That represents a completely pure node. So remember the basic interpretation. Entropy equal to 0 means it is pure. High entropy means greater uncertainty. Now we have learnt about entropy. The next question is, how do you use entropy to select the best attribute? The answer is information gain. Information gain measures how much uncertainty is reduced after splitting the data using an attribute. The formula is information gain equal to entropy of parent minus weighted entropy of children. This is very important formula. Let us consider it conceptually. Suppose the parent node has high entropy. We try to split the data using income. After the split, the child node becomes much purer. Therefore, the weighted entropy of the child become lower. The difference between the parent entropy and the weighted child entropy is the information gain. Therefore, higher information gain means better split. We have decision tree evaluates several attributes. It selects the attributes that provides highest information gain when using information gain criteria. Let us work through an example shown in the presentation. Suppose we have 10 loan applications. There are 6 approved and 4 rejected. Therefore, the initial entropy of the dataset is approximately 0.97. Now suppose we split the dataset using attribute income. After splitting, the high income group contains 4 approved and 0 rejected. Therefore, its entropy is 0. The low income group contains 2 approved and 2 rejected. Its entropy is approximately 0.91. Now we calculate the weighted entropy of the children. High income group contains 4 out of 10 records. So we divide it by 10 and multiply by 0. The low income group contains 6 out of 10 records. So we divide it by 10 and multiply it by 0.918. The attribute income reduces uncertainty by 0.42. If another attribute produces a higher information gain, the decision tree algorithm will choose that attribute instead. The result is approximately 0.551. Now calculate the information gain. The parent entropy is 0.971 and child entropy is 0.551. Therefore, information gain is equal to 0.420. So the income attribute provides an information gain of approximately 0.42. If another attribute gives higher information gain, then that attribute will be preferred. This is how the decision tree makes splitting decision mathematically rather than arbitrarily. Now let us move on to another important impurity measure is Gini index. The Gini index is another measure used to evaluate the impurity of the node. Just like entropy, the objective is to create nodes that are pure as possible. The formula for Gini impurity is Gini is equal to 1 minus summation of Pi square. Here Pi represents the probability of each class. The important interpretation is Gini equal to 0 means a completely pure node. A value closer to 0 indicates lower impurity. A higher value indicates greater impurity. One more characteristic of Gini index is that it is completely simpler than entropy because it does not require logarithmic calculation. The Gini index is commonly associated with the CART algorithm, which we will study in the greater detail in the later module. So, when you remember Gini index, rather than three things, remember these three things: impurity measure, lower is better, commonly used by CART. Let us calculate the Gini index using simple example. Suppose a dataset contains 10 records, 6 belongs to class yes and 4 belongs to class no. Therefore, probability of yes is 6 divided by 10, which is 0.6. The probability of no is 4 divided by 10, which is 0.4. Now we apply the formula. Ini equals 1 minus 0.6 squared plus 0.4 squared. 0.6 squared is 0.36, 0.4 squared is 0.16. Therefore, Gini equals 1 minus 0.52. So, Gini equal to 0.48. What does this tells us? The node is not pure. It contains a mixture of yes and no classes. If all 10 records were yes, the Gini value would be 0. Therefore, the lower Gini value indicates a better and more homogeneous node. So what does this tells? The node is not pure. It contains a mixture of yes and no. If all 10 records were yes, the Gini value would be 0. Therefore, the lower Gini value indicates a better, more homogeneous node. Now we have reached another important part of decision tree construction, which is stopping criteria. The question is, when should the decision tree stop splitting? If the tree continues splitting without any restriction, it can become extremely deep and complex. Such a tree may memorize the training data. This is called overfitting. Therefore, decision trees use stopping conditions. There are several common splitting criteria. The first is pure node. If all nodes belong to the same class, there is no reason to continue splitting. Second, no remaining attributes. If there are no useful attributes left for splitting, we stop. Third, minimum number of samples. If a node contains very few records, further splitting may not be meaningful. Fourth, maximum tree depth. We can specify maximum tree depth for a node. Fifth, the information gain is 0 if the split provides no meaningful reduction in uncertainty. We stop. Stopping criteria helps us control tree complexity and reduce overfitting. Now let us take a simple example to understand the entire construction process. Suppose a bank wants to predict whether the customer will receive a loan. The attribute become income, credit score, and employment status. These are the attributes. The target is loan approved or loan is rejected. Initially, all records are placed in root node. The algorithm creates the impurity of the complete data set. Then it evaluates income, it evaluates credit scores, it evaluates employment status. Suppose the credit score provides the blessed split, therefore the credit score become root node. Now we divide the customer into two groups, for example good credit score and poor credit score. The algorithm examines each group. Suppose the good credit score contains almost entire approved customers, that the node may become leaf node and the loan is approved. The poor credit score group may still contain both approved and rejected customers. Therefore, the algorithm evaluates another attribute such as income. The process continues until the stopping condition is satisfied. This example shows why the decision tree construction is called recursive partitioning. The algorithm keeps solving smaller versions of original problems. Now let us have a quiz on this topic. Which metric is used by CART algorithm? Options are entropy, information gain, Gini index, Euclidean distance. The answer is Gini index. Second question. A decision tree stops splitting when dash. A node becomes pure, maximum depth is reached, information gain becomes 0, all of the above. The answer is all of the above. All these conditions can act as stopping criteria. This is important because stopping criteria controls the growth of the tree and helps prevent unnecessary complexity. Third question, which node represents the first and topmost decision in decision tree? The answer is root node. Root node represents the complete data set and forms the starting point of the tree. The fourth question is, what is the main purpose of entropy in decision tree construction? Options are to calculate the number of nodes, to measure uncertainty or impurity in the nodes, to determine the tree depth, to count the number of attributes. As we know, the answer is to measure the uncertainty or impurity of a node. Entropy helps us to understand how mixed the classes are. Which statement correctly describes information gain? Option A, it measures the depth of the decision tree. Option B, it measures the reduction in uncertainty after a split. Option C, it determines the number of leaf nodes. And option D, it measures the number of training records. The answer is option B, it measures the reduction in uncertainty. The correct answer is option B, it measures the reduction in uncertainty after a split. Information gain is one of the most important criteria used to select a useful splitting algorithm attribute. Remember, information gain equal to parent entropy minus weighted child entropy. Higher information gain indicates a more effective reduction in uncertainty. Now let us summarize what we have learned in this lecture. First, we learnt about the basic structure of decision tree. The root node represents the entire dataset and forms the starting point. A decision node represents the intermediate question to the test. A branch represents the outcome of the decision. A leaf node represents the final prediction. We then discussed the levels and depths. Depth represents the complexity of a tree and length of the longest path of the root to the leaf. We learnt about splitting, then we learnt about impurity and entropy. If entropy is equal to 0 means it is pure node. If entropy is greater means it is impure node. Then we study about information gain, Gini index and stopping criteria. With that, we have reached the end of today's lecture on decision tree terminologies and tree construction. Let us quickly recall the journey we made today. We started with basic structure of decision tree. We identified the root node, decision node, branches and leaves. We understood tree levels and tree depth. Then we explored how splitting works. We learned concepts called impurity and entropy calculations. We then introduced the information gain, worked through the numerical values. After that, we learned about Gini index and calculated its value. Finally, we discussed the stopping criteria and complete the decision tree construction algorithm. So thank you for patiently learning the concepts and watching this video. Happy learning.